then what would I do? So let's say, okay, I've gone ahead, I've set all of my things, I've set my temperature, my pressure, I've run my simulation, and now I finally have this tag.xyz. So if I look at it actually, I can see, okay, time step 500, number of atoms, 1. Box bounds, this just tells us where the box is. And here's the real meat, item atoms X, Y, and Z. This tells us, okay, that tagged atom is at location 14.78 in the X direction, 5.41 in the Y direction, 1.59 in the Z direction. And at each time step, it's keeping track of that. So I can actually just go to MATLAB, and I actually wrote a little script that'll take that function, tag.xyz, and it will open it, read each line, and strip out the actual positions. So if I go ahead and I just run that script, whoops, change folder, run that script, then I end up with this XYZ variable that has all of my various positions in it. So now if I wanted to, let's say I wanted to compute the diffusion coefficient of, let's just do that over a very small range of numbers. So XYZ's rows 1 through 5, all columns. Let's call this T1 equals XYZ's of 1 to 5, all columns. So now T1 is just the locations of that atom at the first 5 time steps. But what we really want to know is the mean squared displacement after a certain amount of time. So what that means is that, first of all, we're going to want this to be, what that means is that we actually want to compute, so let's say D1, let's say mean squared displacement after 1 time step is going to equal the mean of us doing this computation a couple times. So we take T1 at the first time step and subtract T1 at the second time step. And what that gives us is the displacement, although if we want the mean squared displacement, we're going to need to take a sum of squares here. So what this does is we find the mean squared displacement of this atom from its location between time 1 and time 2, and I want to find the average of all the mean squared displacements of time 1. So I'm going to do this for T1 at time between 2 and 3, between 3 and 4, and between 4 and 5. I forgot all my squares. Shoot. And you might not want to do all of this at once because I probably managed to do something wrong here. But yeah, curse it. That closed the sum. That closed that. That closed the mean. come on. No, there isn't. Gosh darn it. Okay, let me try this again. So if I just find T1 of 1 minus T1. Oh boy, okay, sorry about this. So anyways, what I'm doing is just calculating the mean squared displacement of size step 1. So that's, well, of size, I'm not actually sure. I think in this case these are 1,000 picoseconds per each. What? No, I didn't tell you to do that. Arc. I mean, I did, but okay. Alright, so this tells me that I get a mean squared displacement of a single time step of 3.395. But that doesn't tell me anything. I can't get a diffusion coefficient out of that. I need to figure out what my diffusion coefficient is with respect to multiple time steps. So, for example, I also need to know what is the mean of exactly the same thing, except now T1 of 1 minus T1 of 3 instead of 2, because, wait, no. Because essentially what I'm trying to look for is the mean squared displacement after 1 time step, the mean squared displacement after 2 time steps, after 3, after 4, and I mean, I could pick any number of various different time steps, but for now I'm just going to show you guys those. So T1 of 2 minus T1 of 4. T1 of 3. And you can see something else that becomes a problem if we don't have enough data, which is that the numbers of intervals that I have to measure this on become less and less frequent if I don't have sufficient data, which means that some of these are probably not going to be all that accurate. And that's fine for what I'm doing right now, but it's probably going to be more of a problem. So mean squared displacement after 2 time steps is larger than the mean squared displacement after 1. I can do it after 3 time steps, and now I'm looking at T1 of 1 minus T1 of 4. And T1 of 2 is T1 of 5. So you can see I'm basically out of data at this point because I decided I'm only going to do this on 5 points of data. So you would probably be better off doing this with slightly more data. And then finally MSD4, I'm down to a single piece of data. It's just T1 of 1 minus T1 of 5. With that sum squared in there because mean squared displacement. Oops, what did I do? Okay, well, I guess that was a case of me having really bad data there, since you can see that that's smaller than it really should be. But let's just go ahead and plot these guys. So plot versus from 1 to 4, because those are the only time steps we have. MSD1, MSD2, MSD3, MSD4. And I'm going to plot that large. Okay, so we can see we have a plot, and I'm not sure what happened to my last dot. MSD1 should have showed up there, and it did not for some reason. Hang on, let me replot that. Only I'm going to do it without MSD4 for a change. 1 to 3, enter. Okay, what? What's happening here? MSD1 is fine. Okay, I'm slightly confused now. Well, if I do that and then go to my basic fitting, fit a linear equation, I'm not sure why it's not actually showing up, but maybe it's just kind of hiding down at the bottom here or something, I guess. What I can do is I can actually fit a linear equation to my data that I got out of my diffusion coefficient, show my equations, and then I say, okay, that shows me that I have a slope of 3.2. So if I go through and work out, that's 3.2 per, I think it's 1,000 femtoseconds per each of these one. I don't quite know, we'd have to check. That'll get me my diffusion coefficient if I then divide out by, in this case, 6, because that's 2 times 3, so we need to divide it by 6. But then we'd eventually get our diffusion coefficient. And you guys are going to basically be doing that for your homework, but since you won't be, doing this quickly in front of a class of however many people, I'd hope that you would, you're going to be asked to do it a little bit more rigorously than that, even though you're only going to have to actually compute this by hand once.